All right, so in this video, I'm going to talk about can an object have angular momentum if it's traveling in a straight line? Then I'm going to solve an example problem. And so let me describe the problem here, and then I'll answer the question. So the problem is this, is that we have a bullet with a mass of 20 grams. So I'm going to write M little b for the bullet, and then M big B for the mass of the block. And so the bullet is traveling about 300 meters per second straight across like this. It then impacts the wood at the very top right here. And this wood is free to rotate about a pivot point located at the bottom. The wood has a length of 2 meters. And just to make the problem simpler, we're going to neglect gravity. So imagine this is sort of the, a tabletop view of a block of wood. So the block of wood would rotate about the tabletop, not in a vertical way. And so the question is what is the final angular velocity then of the block and the bullet system? And so going back to our first question, the answer is yes, an object can have angular momentum even if it's traveling in a straight line. And the reason for that is because angular momentum all depends on your frame of reference. What do I mean by that? Well, imagine instead of this block of wood right here, imagine that you're just sitting at this pivot point and you see a bullet beginning up here in the upper left corner. You see it kind of go by straight above you and then passes on going to the right. From your frame of reference at that pivot point, it looks like a rotation. Another way to think about it is that if angular momentum is conserved, that's where we're going to start with this problem. The initial angular momentum is equal to the final angular momentum. If that is conserved, and we know that after the bullet embeds itself in the block, we know that that will have some angular momentum. We know that that angular momentum has to come from somewhere. And because this block starts out at rest, that angular momentum must come from this bullet. So that's another way of thinking about it. But the answer is yes, an object traveling in a straight line absolutely can have angular momentum given a certain point of view, a certain frame of reference. All right, so how do we solve for the final angular velocity of the bullet block system after the bullet embeds itself in it? Well, we say that the initial angular momentum is equal to the final angular momentum. So we're going to add up those two angular momentums of the bullet and the block, and then set it equal to the final angular momentum of the bullet block system. And so our equation is the moment of inertia I of the bullet times the angular velocity of the bullet plus the moment of inertia of the block times the angular velocity of the block. This is all the initial stuff, is equal to all the final stuff. Well, once the bullet embeds itself in the block, we no longer have one object, or I'm sorry, we no longer have two objects, we have one object. And so therefore, our moment of inertia is going to be the moment of inertia of the bullet plus the moment of inertia of the block, all times the final angular velocity. All right, so now it's just a question of plugging in what our values for angular velocity and moment of inertia. Well, if our pivot point is right here, and initially the block is at rest, I can say that this entire term then is 0, so that makes it a little bit easier. And so I need to know what is the moment of inertia of the bullet and what is the angular velocity of the bullet. Well, remember that we can say, I'll write it over here, remember that we can say the angular velocity is equal to the velocity over the radius. And so if we want to go between translational stuff like tangential velocity or translational velocity or just plain old velocity, sometimes it's called, and angular velocity, we say, okay, then we just take that velocity and divide it by the radius. What is the radius here? I mean, the bullet doesn't have a radius, does it? I didn't put it anywhere. Well, remember, the radius represents the distance between the axis of rotation and where that object is. So if this is our axis of rotation right here, and we have a length of 2 meters, because remember the bullet's going to impact it right at the top of the block, then we know that the radius, the distance between this pivot point and where the object is, we know that's the same as the length of the block. And so the radius is just 2 meters. But I'm not going to say radius. I'm going to keep it simple and just say that it's equal to length. And the reason I do that is, well, I'll show you in a second, but something's going to cancel out. And so instead of V over R, I'm going to write it as V over the length. All right, what is the moment of inertia then of the bullet? Well, if you have a point mass, which we're going to assume, even though I drew in a little bullet, we're going to assume that the bullet is small enough to approximate it as a point. then you can say that the moment of inertia is simply equal to mass times length squared. So the moment of inertia of the bullet, or of any point mass, is mass times radius squared. In this case, our radius is the length. And so we're left with mass times length squared, and I'll put mb for bullet. And that's multiplied by the velocity over the length. This term is 0, so I'll leave that. Is all equal to the two moments of inertia added together. Well, I know what the moment of inertia of the bullet is. That's simply ml squared, mass of the bullet squared. I'm sorry, mass of the bullet times the length squared. Plus, what is the moment of inertia of this block right here? Well, again, these are things you don't need to memorize. You just have to understand what the formula means. And so the formula for a block, or another way of putting it would be a thin rod. That's sort of what we can imagine this block is. Rotating about an axis at its very end is equal to 1/3 mass times length squared, and that'd be the mass of the block squared. Or, I'm sorry, mass of the block times length squared. And then this is all multiplied by the final angular velocity of this. And so now we have everything we need. We have these values for the mass of the bullet and the mass of the block. We have the length, we have the velocity. We can plug in everything. Before we do that, I'm just going to cancel one of the lengths right here, because there's a length squared and times the length. And so this would simplify down to the mass of the bullet times the velocity times the length is equal to mass of the bullet times length squared plus 1/3 mass of the block times the length squared, all times the final angular velocity. And I want to solve for angular velocity, so I'm going to bring this entire term over to the other side, and I'm left with omega f, the final angular velocity, is equal to the mass of the bullet times the length times the velocity of the bullet, all over the mass of the bullet times the length squared plus 1/3 times the mass of the bullet times the length squared. And now we have values to plug in. So if I plug in these values, the mass of the bullet is 0.02 kilograms. And so that's equal to 0.02 kilograms times the length of 2 meters, that's 2, times the velocity, that's 300, all over the mass of the bullet, so that's 0.02, times the length squared, that's 2 squared, plus 1/3 times the mass of the block, that's 5 kilograms, times the length squared, that's 2 squared. All right, I don't have a calculator. However, plug this value in, and that will be your final angular velocity. And remember, angular velocity is measured in radians per second. Radian isn't a unit, it's sort of a placeholder. And so whatever answer you get will be in radians per second. And that is your answer of the final angular velocity of the bullet and the block system.